Hello, everyone. Today we're going to continue our discussion of molecular analysis and organic chemistry by talking about infrared spectroscopy. IR spec is probably one of the most common and most useful tools in the organic chemistry lab. It is a relatively inexpensive instrument. It's fast and it tells us basically which functional groups are present in a molecule. So imagine, for instance, that you're trying to do a reaction in which you're converting an alkene into an alcohol. It's very easy with IR to monitor the progress of that reaction to determine if the alkene group is being replaced with the alcohol group. And so these are present in virtually every organic chemistry laboratory. This is a typical FTIR or Fourier transform infrared spectrometer. We've got a computer off to the side. We have our instrument itself. And basically what this is set up to do is to generate light in the infrared spectrum, pass that through or with this attachment, bounce it off of a sample, and then detect which parts of the light are either reflected or emitted, or sort of passed through the sample. And based on that pattern of what's been absorbed and what has passed through, we can determine what functional groups are present in the molecule. This particular instrument has a solid sample attachment. You may find them with this attached, or this entire piece can come out and we can put samples in a different kind of a sample holder to do liquid samples. So at its core, IR is a spectroscopy technique. And in general, spectroscopy involves bombarding a sample with light in a particular region of the spectrum. So we could talk about visible spectroscopy, we could talk about ultraviolet spectroscopy. In this particular case, we're talking about infrared spectroscopy. And even more narrow than this, we're talking about the very near infrared, so sort of closest to the visible spectrum here. We are bombarding a sample with that wavelength of light or a number of wavelengths of light in that region and looking at which ones of those are absorbed. If we diverge for a second into physics, we can think about how energy really is a stream of particles, of photons moving in this wave formation. And so we can talk about how high energy light has a short wavelength or a relatively high frequency, meaning that if you were an observer standing at a particular point as this wave is going past, you would be hit quite frequently by those particles. This is violet. Ultraviolet would be even tighter than this, something in the 300 or high 200 nanometers. The visible spectrum goes from roughly 400 up to about 800, where we run into the reds. We can see that sort of on this diagram. And then infrared goes beyond that. So we're talking about 800 plus nanometers of wavelength, or frequencies here on the order of 3 to 4, kind of a range, times 10 to the 14th per second. We have a couple of physics equations here, energy related to frequency, and so a higher frequency would give us a higher energy wave, and wavelength and frequency inversely related. So higher wavelength means a lower frequency and vice versa. There's some terminology involved with waves. This is basically from physics, but you can look at these terms here. Typically, when we're talking about the kinds of waves that we're dealing with, we're going to be talking about the nanometer, or rather hundreds of nanometers of frequency. So as I mentioned, visible is roughly 380, 400 nanometers up to about 800. Infrared is just a little bit larger wavelength than that. The organic region of IR is really quite narrow. So we're going to be talking about, if this entire region here was labeled previously as infrared, we're really talking about this area from about 2.5 micron wavelength up to about 25 microns. These are represented a little bit differently on the graphs that we're about to see. They're represented as something called a wave number. And so wave number here is represented as 1 over the wavelength. And so it's not exactly the same as frequency, which is why it doesn't have quite the same symbol. but it's still, we can sort of think about it as that sort of a measure. So our wave numbers on our readouts are going to go from about 4,000 down to about 400 per centimeter. And that can be shown here on a typical organic molecule infrared spectrum. To orient you to this kind of a display, we typically see these represented in transmittance. And so something with 100% transmittance would not absorb at all at that wavelength. So all the light of that particular wavelength is passing through the sample. As the sample absorbs some light, we would get a decrease in transmittance. So less light is able to come through. And so we get these features on the chart, which are called peaks, even though they point downward. So we see a peak here, for instance, at about 3,300 wave numbers. Typically, these, as I mentioned, are going to be oriented from about 4,000 down to about 400. And we can see these peaks of different shapes and different intensities, and all of those are indicative of something, as we'll see in the next several slides. But what is actually absorbing? Well, what's actually happening when we bombard these samples with infrared radiation is that the molecules are interacting with that energy. And so we get basically two fundamental kinds of interactions. We get stretching interactions, whereby a bond here, remember we can sort of think about bonds as being like little molecular springs holding atoms together. You could imagine this spring, this bond, stretching as those two atoms move closer to or further apart from one another. If that happens in a symmetric way, we get symmetric stretching. If it happens in an asymmetric way, we get asymmetric or anti-symmetric stretching. We also can get bending. So imagine now these three atoms in particular connected by little springs. You could think about sort of wobbling these outer atoms relative to that center position. So in plane, meaning that they're sort of in the same planar structure. Out of plane, meaning that they're in two different directions. All of these happen with all of the molecules that we're going to see. But the key thing is that different bonds absorb energy at different frequencies. And so when we look at a typical absorption, we'll see charts and charts and charts. Every textbook and every reference source has a chart of IR absorptions. What we'll see is that there are particular absorptions that are characteristic. So for instance, if we have an alcohol group in the molecule, that OH bond absorbs energy around the 3,200 to 3,500 wave number kind of a range. Furthermore, an alcohol, due to hydrogen bonding, typically has a little bit of a diffuse broad band that shows up. If this was a particularly sterically hindered alcohol that couldn't do hydrogen bonding very well, this peak would be in the same basic place, but it would be sharper. Almost every organic molecule will have some carbon-hydrogen and carbon-carbon single bonds. Those show up as relatively sharp but overlapping peaks just south of 3,000 wave numbers. So there is a lot of stuff going on here, right? This is the infrared absorption spectrum for ethanol. Ethanol, if you recall, has two carbons. It has a handful of hydrogens attached to those carbons, and then it has an OH group. There are a lot of atoms and a lot of bonds to think about doing different sorts of stretching and bending and twisting motions. And so we get a lot of absorptions. Just like in the case of mass spec that we talked about previously, you don't want to spend your time sort of trying to figure out which absorptions come from which particular interactions. It's not as useful an exercise as you might think. What we're looking for are patterns, and particularly these very indicative patterns like the OH, this broad stretch that happens in the mid-3000s. So as we see in every textbook, we will have a chart that provides sort of a summary of these sorts of important interactions. You'll see in this chart, and this is from our textbook, but there are others that have different levels of detail in different textbooks and references. Singly bonded alkane molecules typically have absorptions just below 3,000 wave numbers, and those are in the medium sort of intensity. These are not particularly useful because all organic molecules have those kinds of interactions, and probably if the molecule has any kind of complexity to it, you'll have different particular types of CC and CH bonds. And so you'll get an overlapping kind of mess of peaks around that neighborhood. What's more interesting to us are these functional groups. So what this table is showing us is that for an alkene, for instance, a terminal alkene, or an alkene that has a carbon-hydrogen bond, a hydrogen attached to an alkene carbon, we will see a peak showing up a little bit higher than it would for just an alkane. So we'll see a peak showing up just above 3,000 wave numbers. Similarly, the double bond itself, the CC double bond, will show up as a pretty well identifiable peak around 1650. Alkynes have a similar pattern. If it's a terminal alkyne with a hydrogen, we'll see a strong peak around 3300. That's a good one to remember. The triple bond itself shows up around 2200. We have similar peaks for lots of different groups here. Some of these will be particularly useful, as we'll see in a little bit. Some won't be as useful. But the things that you want to pay attention to are those that are really identifiable. So the OH group giving a strong, broad peak around that 3500 mark. That one is really characteristic. So that will indicate that you have an alcohol, or if this is a real sample that you've made in the lab, maybe it's still a little bit wet from the aqueous workup that you did in one of your last steps. Maybe it has to dry. That's pretty common. CO bonds, which would be part of an alcohol, of course, but also could be part of an ether, those will show up around 1100. Sometimes those are useful, sometimes they aren't, and I'll show you why in a couple of slides. Aromatic rings tend to have sort of a mess of peaks that I'll show you in a little bit. These are sometimes useful. We sometimes call these overtones because they're a combination of small peaks that are together sometimes useful, but individually hard to see. The amine group shows up in roughly the same place as the alcohol group. So whether we have an OH or an NH, we'll see that. I'll show you that the NH resolves a little bit differently than the OH. Carbonyl compounds in general terms show up between 1650 and 1750 or so, but we can actually distinguish what context that C double bond O is in based on the specific positioning. So while it might seem like splitting hairs, whether a peak shows up at 1710 or 1730, for instance, that's actually a useful characterization to help us distinguish between two, sort of similar structures. Carboxylic acids are worth noting because not only do we see the C double bond O peak around 1710 as a nice sharp peak, we also see that broad, strong peak that we would think of as characteristic of an OH. But when it's tethered into the carboxylic acid group, we get this wide plateau that's really characteristic of a carboxylic acid. And so I'll show you what that looks like in a little bit. There are a couple other ones here that you might find as you're going through things. Again, every textbook has a slightly different combination of these features that they list in their table, but this one will do you pretty well as you go through the homework. So here's an example. At the top we have an alkane. And so we can see that that sample is relatively boring. I have that conglomerate of peaks here around just under 3,000 wave numbers. This is a combination of all of our different CC and CH peaks kind of overlapping each other in this neighborhood. And then we see a bunch of other stuff down here. And if you go back and look at the table on the previous slide, you'll say, well, I didn't really identify much of what's going on in here. And we'll get to that with this concept of the fingerprint region. Just like mass spec, modern IR instruments have the ability to use computational analysis and database matching to help us differentiate between some really similar molecules. For you and I doing this by eye, there's not as much that we can really accomplish down here in the fingerprint region. So most of the time in the laboratory when you're using this technique, you're not going to be looking at anything below about 14 or 1500 wave numbers. But if we look at what we can see here, these are all 6 carbon molecules, just all single bonds. We have a double bond, we have a triple bond, and we can see those differences. While they all have the alkane kinds of bonding in this conglomerate of peaks around 3,000 or just under 3,000 wave numbers, we can see that terminal alkyne showing up as a nice sharp peak just above that point. This one's around 3100 or almost 3100. When we sort of upgrade that to a triple bond, we see that shift over a little bit further. And so those sharp peaks are characteristic of having a terminal alkene or alkyne. Likewise, the multiple bond between the carbons can be seen here. The double bond here just a little bit above 1600, and the triple bond is a nice sharp peak around 2200. In general, our singly bonded bonds, our single bonds are going to show up pretty much around 2800 and above. We'll have our triple bonds just below that. So if you go back and look at the table, the alkyne and the nitrile both show up in here. And between about 1500 and 2000, that's where we'll see our alkenes, our carbonyls, and our double bonds to nitrogen. So sort of single bonds to the left, triple bonds in the middle, double bonds in this intermediate region. And then the fingerprint down here that's not super useful to us, but can be super useful to computational analysis. So as an example, a typical sort of a question might say, here are these two molecules that have the same formula. So both of these are 3 carbon molecules with a double bond, so 1 degree of unsaturation. They both have an alcohol. They both have an oxygen. One of them is a ketone and one of them is an alcohol. So how can we distinguish them by IR spec? What we want to think about is those structures and look for functional groups that are different. So most obviously is this ketone here in the acetone molecule. If I go back and look at my table, I'll see that ketones show up in that carbonyl range. So in the 1700 kind of a range. And specifically, a ketone should give me a strong peak around 1715. Now, if I look at my other molecule over here, I don't have that molecule, that functional group. So I can certainly say I wouldn't have a peak at 1715, but what would I have? Well, I have a hydrogen bonding capable alcohol here, so I should have that broad characteristic peak around 33 to 3500. And I've got the double bond, the alkene, that's terminal, so I should have not only the CC bond around 1650, I should also see that CH bond just above the alkane region. And so when I go and look at these, here are my two molecules. These are real lab spectrums, so they're not as clean maybe as something you'd see in a textbook. But when I look at my alkene alcohol, I can see those bonds. The CC double bond here is that sharp peak between 16 and 1700. I can see the broad sweeping hydrogen bond alcohol peak over here in that 33 to 3500 range. If I look carefully, this little blip right there is probably the CH alkene bond. Just showing up just between 3000 and 3100. It's largely obscured by the wide hydrogen bonding peak from the alcohol, but I can see it sticking out there. If I didn't see that, I wouldn't necessarily panic. Because the alcohol is such a broad peak, it can often obscure some of the detail in this area. Now, in the case of the ketone, I don't see that stuff. What I do see is this monstrously strong peak for the ketone. The textbook says that should be 1715. I'll let you make a judgment here, but it's just above 1700. Now, I do see a little bit here in that hydrogen bonding alcohol region, and I'm going to bet that this particular sample was a little bit wet, had a little bit of dissolved moisture. Maybe it was a humid day in the lab when the sample was taken, but that could be a little bit of residual water kind of hanging out in the sample. All right, so other questions you might see at this point are things like this. So just asking you to get used to that table. I don't think it's necessarily useful to memorize a table like the one I showed, but it is useful to have it handy, and it's useful as you go through problems to get familiar with certain common absorptions. So again, the idea here, well, what might have a strong peak around 1710? That's going to be one of our carbonyl groups, probably a ketone or an aldehyde. 1540, there's almost nothing listed there except for the nitro group. So that's one that might be useful, particularly when you start talking about aromatic compounds. Strong absorptions here. Now, this is two different absorptions. Again, 1720 is in that carbonyl range, and this broad peak here, that's a dead giveaway for carboxylic acid. So let me show you what these look like. If I look at a simple nitro-containing molecule like nitropropane, we can see normal alkane, CC, and CH stuff here. Really strong peak around 1550, 1540 kind of range for that nitro group. Other example problems might say, how could you use IR spec to distinguish something? This is kind of like that acetone alcohol version that we did a little bit ago. But in this case, here we have an alcohol versus an ether. Well, what's different? They both have the CO single bond here and here. Between the C and the O in both molecules, we have a CO single bond. So that particular peak wouldn't change. The difference in structure is that I have this OH bond in the alcohol and I don't have it in the ether. And so I would expect to see that large peak. If I look at these two, both 6-carbon hydrocarbons with 1 degree of unsaturation, one is a cycloalkane and one is an open chain alkene. What's the difference? Cyclohexane is entirely alkane, while this one has that double bond. And so I would expect to see that CC double bond here. Since this is a terminal alkene, I might also see that the CH peak from the alkene showing up just above the alkane stuff. And then down here, I've got a carboxylic acid versus a molecule that has both of the parts of the carboxylic acid group, but separated. This is an alcohol on one end of the molecule and an aldehyde on the other. All the atoms are the same here, but the arrangement is different. So carboxylic acid, I would see that broad peak for the alcohol shifted a little bit down on the spectrum. Rather than being the standalone alcohol around 3500 and the standalone aldehyde, which I didn't write here, that would be down in that 1710 to 1750 kind of range. The carboxylic acid is going to have that OH group spread out really widely. And here's an example of what I'm talking about. Again, this is a real spectrum, so it's a little bit messy, but propanoic acid is our 3-carbon carboxylic acid. It's actually this one right here. And I do see now that broad peak, sharp, strong peak around 1700 plus for my carbonyl group. But I see that coupled also with this very wide peak. These two together are characteristic of that carboxylic acid, rather than a standalone aldehyde or ketone and an alcohol that would be down here if it was by itself. I'm seeing this wide, broadened peak. And so here's our table again, right? Just keeping in mind here, now that we know about the fingerprint region, now that we know about some of these other things, we can see that IR isn't particularly useful for helping us out with alkyl halides. These show up in the fingerprint region. The computer can help us identify these, but it's a little tough for us to do it by eye. But the rest of these are pretty useful. And just to run through them one by one, alkanes, again, the CC itself and the CH, both are relatively non-useful sorts of absorptions. We can see the IR for a standard, just a plain old alkane as not being particularly exciting. So again, we see this mess of overlapping peaks around 2900 or so. That's pretty characteristic of an alkane. Nothing else going on here. When we add in our double bond, we see a couple of characteristic peaks. So the ones that we'll be looking for by eye are going to be the CH, if there is a hydrogen connected to an alkene carbon, or so-called vinylic hydrogen. We'll see that as our sharp peak around 3100. The CC double bond itself should show up as a pretty strong, medium intensity sharp peak around 1650. We will likely not see these other substitution patterns down here. What this is getting at down here is that if we have a mono or a disubstituted alkene, we'll get certain kinds of bending that can be detected as far as sort of determining whether it's one isomer or another, for instance. And those are, again, more for computer analysis than for analysis by eye. All right, but here's a couple of these spectra. So 1 pentene and 2 pentene, both of them show us a sort of CC double bonding peak around 1600 plus. This one's a little smaller right here, but it's there. But what we see in the terminal alkene, we have a stronger CH alkene, the vanillic hydrogen peak here, than we see over here, right? This guy would still have one of those hydrogens. This one's got two. All right, alkynes, we mentioned. Again, we see the carbon-carbon multibond showing up now in that triple bond region, around 21 to 2200. And we see the CH, if it is a terminal alkyne, we'd see that as a nice sharp peak around 3300. Here's some real examples of that. At the bottom first, an internal alkyne, we see not a whole lot of exciting stuff, right? We should be looking for that 21 to 2200 peak. A little bit of something going on in here, not particularly exciting, but we don't see the CH peak over here. Now in the 1 pentyne, the terminal alkyne, we see a little bit better that C triple bond C peak. We also see that CH peak. And this one's really useful to determine if other data has told you that you have an alkyne, for instance, and you wanted to figure out which one. Seeing this peak at around 3300 is really characteristic of the terminal alkyne. All right, aromatics. These are tough. What we're going to see here is the hydrogen, carbon-hydrogen bond on an aromatic ring typically shows up just above 3000, and it's a weak absorption, and typically there's other stuff there. So if the molecule has anything else going on, it probably will be lost in the other alkane stretches that we're talking about. The CC bonds themselves, the aromatic CC bonds, are going to show up as a collection of small absorptions around 1600 or so. So again, unless the IR is very clean, you may not see these. If we look at an IR of just benzene, which is just the aromatic ring, maybe we can convince ourselves we see that CH bond right here, although you can already see here there's a number of things happening to kind of obscure this area. And then the other peaks for the aromatic ring carbons should be in the region here of 1600 or so. It's kind of what we're seeing through here. So a collection of small peaks, again, not very useful, but you'll hear them described as aromatic overtones. Alcohols and amines are the real showstoppers of the IR world. They both show up as pretty intense peaks. And they're both going to be just about the highest thing you're going to find, so in that 3500 kind of a range. Alcohols tend to show up as very broad peaks, particularly if they can accomplish hydrogen bonding. So primary alcohols, secondary alcohols, even tertiary alcohols that aren't too bulky, you'll see a broad peak in this neighborhood. If we had a very bulky alcohol, so imagine maybe a tertiary alcohol that has 3 aromatic rings as the 3 substituents on that alcohol carbon, that one would be more of a sharp peak because it can't hydrogen bond very well. It'd still be in the same area, it'd still be obvious, but it wouldn't be as broad. Unfortunately, water also has this OH structure and is quite capable of hydrogen bonding. So in a practical sense, if there's any water in your sample, it will show up out here as a pretty obvious peak. And then you'd want to think about drying your sample or considering whether it actually does have an alcohol in it. The NH bonds show up in the same area as well. They tend to be sharper. And what's really cool about this is that you can tell how many H's are on a nitrogen based on what you see. So if I have a single H, so maybe I had 2 carbon groups here and just the 1 hydrogen, I would see 1 peak. If I had 2 hydrogens connected to the nitrogen and just 1 carbon group, I would see 2 different absorptions in the same area for the two different H's. And so we can see that if we look at simple alcohols and amines, here's one propanol at the bottom, 3-carbon alcohol, and we see that gigantic broad peak in that 33, 34, 3500 wave number kind of a range. In propylamine, we see a couple of things. So we see the CN bond down here that I didn't even mention because it's in the fingerprint region, but we see the NH bonds here. Propylamine has a terminal nitrogen, so we have two NH bonds, and so I'm seeing both of those, which is kind of a neat thing. That's pretty typical of an NH2 group somewhere in your molecule. So if I were to combine these, for instance, so what if I had this one molecule that had both an amino group and an alcohol group? Well, what would that look like? And so here's an example of one of those. You could draw out this structure, but I have a 3-carbon alcohol that's got a couple of branches on it. And so when I look at this, well, what am I seeing? Yes, I see an alcohol group here. That one's pretty easy. If you look carefully, you could maybe justify a little peak there that might say there's something else going on. That's actually going to be our amino group kind of poking its head through, even though it's mostly obscured by the alcohol. So how do I know the amino group is there? Well, I still see it down here. And so this is a case where the fingerprint can be useful, again, particularly with computerized analysis. Carbonyl groups, the C double bond O shows up in pretty much the same spot. If you wanted to be very general, you could say 1650 to 1750 as a family. But we can see there's a little bit of difference that aldehydes tend to show up around 1730 if they're all by themselves, around a little bit lower number, closer to 1700 if they're resonance stabilized by a nearby double bond or by an aromatic ring. We get ketones, again, showing up a little bit different range, but pretty close to aldehydes here. I've got esters now showing up, another ester structure over here. So lots of different structures with their particular absorptions. But the point of the slide is to say, if you see a strong peak in that 1650 to 1750 kind of range, you'll want to think C double bond O. As a real example, here's acetone. So acetone is right here. So the textbook would say 1715, and we see that strong peak here. This is the same one we saw earlier with maybe a little bit of water in the sample. If I look at an aldehyde instead of a ketone, I can see that peak is in, to my eye, pretty close to the same place. But if I sort of click back and forth, you can see how it shifts just a little bit. If I go to an ester, I see that it shifts a little bit further, right? So we're going from 17, 15, 20, 30, maybe up to 1750 now, going to the ester. And so I don't expect anybody to memorize all of these, but when we look at the table overall, we see that carbonyls in general show up in 1650 to 1750, and that's super useful. We can easily distinguish that from a C single bond O and from an alcohol. So if we look at an IR spectrum for a particular molecule, we can tell very, very quickly which one we're looking at based on these kinds of patterns. So most of the sort of real spectra that I showed you today come from this spectral database for organic compounds, SDBS, which you can click on this link to go to, or you can just Google for SDBS. This particular database, if I can pull it up here for you just a second, when you click that link, you will come to a page like this. You have to agree to their terms. And then it will come up and ask you to put in a compound name or a formula or a range of molecular weights or numbers of atoms. There's lots of different ways you can do this. But for instance, if I said I wanted to look at butanol as a name root, I click search, and it will come up with a whole bunch of stuff that's been distributed into this database. So 2-butanol and 1-butanol, for instance. Here's another molecule that, well, it isn't actually a butanol, it's an isomer of that. And I can see that this has a lot of different information. So mass spec data, IR that we're talking about in this video, NMR, that's the topic of another discussion, and then Raman is another kind of instrumentation, another kind of analysis that someone could do. If I click on 2-butanol, for instance, I look at the IR, I will see a reading like this that shows a real spectrum. Again, butanol, the only important functional group is that alcohol, so I see that here. I can see sort of the wave number and transmittance values for each of the peaks if I wanted to get, strong numbers for this, and it'll show me a structure. I can also click over here and see the other kinds of data that are available for that molecule. So this would be the mass spec for it. We can look at carbon NMR. We can look at hydrogen NMR. In this particular case, there are two different IR samples that were provided. One in a solution of carbon tetrachloride and one as a pure liquid. If it's available, the pure liquid film is the one you'll want to look at. It's going to have the fewest artifacts from, in this case, the carbon tet as the dissolving agent. So this database can be particularly helpful when you're trying to go through all of your different samples and practicing and looking at real life examples. Remember that these are real spectra, and so they can be a little messy sometimes because sometimes that's what real data is. But they do provide a lot of good information. And so with that, the best way to practice this is just to do problems. So go into the textbook, go through the back of the chapter, go through the examples in the text, practice and practice and practice, and try to get down this idea of how to use this information in a really functional way. As I said, don't stress a lot about memorizing every single little bit, but get used to first where these different groups show up, practice identifying them, and after you've got that down, then you can start to try to do a little bit more of this fine level differentiation. So with that, that's IR spectroscopy in a nutshell. In a separate video, we will finish out our molecular analysis by talking about nuclear magnetic resonance, or NMR spec, as well as ultraviolet spectroscopy that looks at conjugated systems. So until then, good luck, keep up the good work, and I will talk to you again soon. Bye, everyone.